So this sheet titled Breeding Familiarity with Current Electricity. Basic bunch of problems once again. The first problem is about a very ordinary network comprising 3 resistors ABC. This is 30 ohms. This is 30 ohms. And this is 30 ohms. And across A and B, there is a battery, 2 volts connected like this. We want to find the current flowing through the battery. We want to be able to find the current flowing through the battery. Now, very simple. This current I will pass across this as I1 and will pass across this as I2. I2 would be the current flowing this way. I1 would be the current flowing this way. They would come and merge at B and will flow as I through this battery. So I is I1 plus I2. Now, as far as I1 is concerned, it's connected across a 2-volt battery. 2-volt battery against a 30 ohm resistance would give you current I equal to 2 by 30. I1 is 2 by 30, which is 1 by 15 amps, right? Similarly, I2 is flowing across 60 ohms, but drop is 2 volts only. So I2 is going to be, drop is 2 volts against 60 ohms. That means 1 by 30 amps. The net current I is going to be I1 plus I2 is going to be the net current I flowing through the battery. I'm assuming you would have certainly got it right, right? The second problem is about a curved rectangular bar that forms a resistor. A curved rectangular bar that forms a resistor. The curved sides are concentric circular arcs. These are concentric circular arcs. These are the bounding radii, they meet at O, and these concentric circular arcs subtend, let's say, subtend an angle theta at the center, right? This is the wire. This is the wire. Now, the rho is the resistivity of the material of the wire. That's a property, right? Resistivity. And L0 is the length of the inner arc of radius R0. This radius is R0 and this length is L0. Very clearly, L0 is R0 theta. So theta is known to us as L0 by R0. And R0 plus B is the outer radius. That means this length is B units. This length is B units. Now, what is it that it means by a rectangular bar that forms a cross section? We need to find the electrical resistance across its rectangular ends. What it means is, this is one view. You're viewing it like this, but current is flowing this way. You know, this cross section, that means when you observe from here, this is the cross section through which current enters, and this cross section is rectangular. This cross section is rectangular. Do you understand this? This cross section is rectangular, right? So current is flowing through a cross section which is rectangular, Now, do you understand that? That means when you see from here, from the side, the current flows through a rectangular. It's rectangular all through. That means if you cut open this portion, you'll see a rectangular cross section through which current flows. That's given. We now want to be able to find the resistance of this. We now want to be able to find the resistance of this. Now, what really transpires in the process is this angle is theta. I take a length of the wire like this, a circular length like this. I take a circular length like this of radius r and of width dr. This is radius r and of width dr. I take current flowing through this. I take current flowing through this shaded portion. Right? Now, as far as the shaded portion is concerned, what's the area of cross section associated with the shaded portion? B. dr into B. B, is that the width? No. There must be a width given. The width given is A. That means, you know, this length is A. This is the width. What goes into the plane of the board is A units. What goes into the plane of this board is A units. Now, the area of cross section of this is A into dr is the area of cross section through which the current is flowing. Do you understand that? A into dr. Dr is along this direction and A is into the plane of the board. That's a rectangle of side A and dr. That's the area through which current is flowing when I mark this. Do you all understand this? No, you don't understand this, Ayush. Cuboidal? The cross section is a rectangle. When I cut it open like this, I see a rectangle like this, of this width being A units. So what goes into the plane of this is this which is dr. That means when you view this cross section from here, you see a rectangle. You see a rectangle. dr by A is the rectangle that you see as the cross section of the shaded portion. When you cut this cross section, what you see is a rectangle A by dr. What you see is a cross section A by dr. So current is flowing through the cross sectional area only, isn't it? So the area of cross section of the shaded portion is going to be A into dr, through which current is flowing. Current is not flowing like this. Current is flowing this way, A into dr, right? So the resistance of this portion, resistance of this length is going to be specific resistance, which is rho into the length. How much is the length? R theta. R theta is the length of this conductor. R theta SL divided by the area of cross section. The area of cross section is A by dr. A into dr is the area of cross section. SL by A. Right? That's the resistance. Now do you realize this conductor comprises of several such resistance between the two ends, with R starting from R0 and going all the way to R0 plus B. Yes or no? And all these resistors are connected across the same 2 points. That means the potential drop across all these R's is the same. That means all these R's are in parallel. These resistors are all in parallel. Right? So if they are in parallel, the reciprocal of the equivalent resistance would be sum of the reciprocals of the constituent resistances. This is the resistance of the shaded portion, D capital R. The reciprocal of this resistance is A into dr divided by rho R theta is the reciprocal of this chosen resistance, right? The sum of the reciprocals of all the dRs, sum of the reciprocals of all the dRs is going to be sum of all of this. Integrate this, where R runs from R0 to R0 plus B. R runs from R0 to R0 plus B. And that will give me 1 by R equivalent. That will give me 1 by R equivalent. Yes or no? Because they are in parallel. All these dRs are in parallel. And why are they in parallel? Because see, look at this resistance. Look at this resistance. They are connected across the same ends. That means the drop in potential is the same. If the drop in potential is the same, they are in parallel. Right? This is 1 by R equivalent very clearly. A by rho theta will come out. A by rho theta comes out. And 1 by R dr is log R. Integrate this, you get log R0 plus B divided by R0 is what you get as 1 by R equivalent. And this theta you can replace by L0 by R0. This theta can be replaced by L0 by R0. So this theta L0 by R0. This is 1 by R equivalent. So R equivalent will simply be the reciprocal of this. Rho L0 by A R0 into log R0 plus B divided by R0. That's the resistance of this conductor. Yes or no? This is 1 by R equivalent. R equivalent be by this divided by log. Right? Confusion? I don't have a problem explaining this again if you require. Shall we proceed then? This? Yeah, of course. See, I've chosen a conductor like this, right? Of length R theta. The length of this conductor is R theta. So, to find the resistance of a conductor, what is it that we need? We need the length, which is R theta. And we need the cross section through which current is flowing, right? Now, if you look at this, you know, current is leaving this way, for example. And when it is leaving through a rectangular cross section. Its thickness is dr, and its what goes into the plane of the board is A units. So this is a rectangle A into dr, right? So specific resistance into the length L, SL by A, area of cross section. That's the resistance of this chosen shaded conductor? No? That's the resistance of this chosen shaded conductor. And the reciprocal of this resistance was this. Why did I choose reciprocal of this resistance? Because all the resistances that I encounter from R equal to R0 to R0 plus B are these concentric conductors, right? Are concentric conductors. And they are connected across the same two ends, right? Whether I choose a conductor this way or I choose a conductor this way. All these resistors are in parallel because across their ends the drop in potential is the same. So I need to add the reciprocal of all these resistances so that I get the reciprocal of the equivalent resistance. That's what we do for resistors in parallel, and that's exactly. So I chose dr, and the reciprocal of this d capital R is this. And I summed up all the reciprocals of this drs, where R runs from R0 to R0 plus B. I got the reciprocal of the equivalent resistance. And theta then was L0 by R0, plugged in AR0 by etc., and then integrate this. SL by A, that's the resistance of a conductor, ohmic conductor. Yes, it is obtained by experiment. SL by A, specific resistance into length. I thought this was all 9-10 stuff really. Yeah, it is, yes, it is obtained through experiment. It is obtained through experiment. Double the length. No, it is also obtained theoretically as well. I mean, it can be proved theoretically as well. But shall we move? Of course not. हाँ हाँ, then you could have done. So I would have taken this cross section in series with this cross section in series with this cross section. You could have done that. No, there is a problem with that, and you need to identify what the problem is. Your expression written is not right. Your expression written is not right. Check that. Shall we proceed? You would have had to take thicknesses like this, an area of cross section. So you would have had to take this thickness into area of cross section. This is what you would have had to take. Number 3. This is the circuit we have. A and B are essentially the same. Then we have the junctions C and F, D, E, etc. Same. Take the potential to be 0 at the negative terminal of the battery. This is 0. How does it matter though? Potential at F is higher or at C is higher? That's the question to be addressed in principle. In principle, we need to know whether current will flow from C to F in this circuit or from F to C. It's not a balanced Wheatstone bridge. Agreed. Yes, it's an unbalanced Wheatstone bridge. Oh, so you know that? Okay. So which is higher? F is higher. Okay. Very good. I'm so happy. Okay. So I have discussed that in my concept class, is it? Which one would be higher? Okay. Then let me add a question to this. If this is 0 volts, how much is VF by VC? It then has to be a number greater than 1. But how much is VF by VC? That's the next question that I want. Given that this is 0 volts, how much is VF by VC then? Let's exactly obtain VF by VC. Right? So, suppose this is VF and this is VC. And this is 0 volts, this is also 0 volts, right? VA and VB both would be the same X volts, isn't it? Both would be the same X volts. A and B are electrically the same, so both are X volts, say. Clear? I need to find VF by VC, the exact number. The direction of the current, yes, we could find from those considerations which we discussed. But now, what is VF by VC? That's the next thing to take care of. Okay. Let me look at this junction C. At C, the algebraic sum of the currents leaving must be 0, right? So the current leaving from C to D is going to be Vc minus 0 by 2R. Yes or no? Vc minus 0 by 2R. The current, algebraic current flowing in this direction would be Vc minus X divided by R. The current flowing in this direction is Vc minus Vf by R. By R. And all of this must add up to 0. That's for junction C. That's for junction C. Yes or no? Let's just simplify this to we get Vc plus twice Vc minus X plus twice Vc minus Vf is 0, right? Multiplying by 2R throughout. So we get 2Vc plus 5Vc minus 2Vf equals 2x, right? That's as far as junction 2 is concerned. Yes or no? Let's look at junction F. Let's look at junction F. Now again, algebraic sum of currents in all directions is going to be 0. What's the current in this direction? Vf minus 0 by 4R. What's the current in this direction? Vf minus X by R. Right? Vf minus X by R. What's the current in this direction? Vf minus Vc by R. And this must add up to 0. Right? Now multiplying by 4R throughout. So we get Vf plus 4 times Vf minus X plus 4 times Vf minus Vc. That must be 0, right? So this gives me like a minus 4 Vc and then 9 Vf equals 4x equals 4x. That means this must be twice this because this is 2x and that is 4x. So this expression must be twice this expression. I hope I have not made any mistake there. Right? So which means twice 5Vc minus twice Vf. This is 4 times x, right? Twice of 5Vc minus 2Vf, and that must be equal to this 4x, which is minus 4Vc plus 9Vf, right? So this gives me like 10Vc, 14Vc equals 9 plus 4, 13 Vf. So Vf by Vc is 14 by 13. Got it? Shall we proceed? So this computation enables getting the ratios as well, numerical value of Vc and Vf. Can I wipe this off now? Let's look at number 4. Problem number 4. The problem number 4 is a network of this kind: 1 ohm, 1 ohm, 1 ohm, 1 ohm, 2 ohms, 13 volts, and it's labeled as A and B. And we want to find the potential difference, VA minus VB. We seek to find VA minus VB in this problem. Right? Obviously, once again, it's not a balanced bead stone. It's not a balanced bead stone, right? Nevertheless, if this is looked upon as 0 volts, how much is this? 13 volts. Yes, absolutely. This is 13 volts. This is 13 volts. Algebraic sum of currents leaving junction A must be 0. So this algebraic current, this and this must add up to 0. So from here to here, VA minus 13 by 1 plus VA minus VB by 1 plus VA minus 0 by 1 equal to 0. That's for junction A. That's for junction A. Right? Same thing we can do for junction B. This plus this plus this algebraically must add up to 0. So this is VB minus 13. VB minus 13 divided by 1, right? This current. VB minus VA by 1. Plus VB minus 0 by 2. VB minus 0 by 2. Two equations, two unknowns. You can solve for VA and VB and therefore find VA minus VB. Got me? See, if I selected this as 20 volts, this will become 33 volts. VA will become this VA plus 13, VB will become this VB plus 13, or whatever 20. Everything will increase by 20, but the differences will remain the same. The differences VA minus VB will remain the same. You know what I'm saying? I'll repeat. Because there is no concept of an exact potential, dude. That's the whole idea in electrostats, electrical physics. It's the potential difference. I mean, I can label any point as any potential, and then based on that reference, I can assign potentials to other points or other regions. Right? Is there anything like an absolute potential? No, there never was. Again, I was hoping that you'll get it right all by yourself, right? Okay, now we have a network in problem number 5. This is 5 ohms, 15 ohms, oh 5 amp current है. Okay, 5 amp current, there is 5 amp current, the resistance not known. Then there is this 5 ohms here. There is R here. There is a battery like this, 100 volts. There is 3 amps going this way. going into a resistor. Fine. There's 3 amps like this. There is 2 amps going through, again, some unknown resistance here. This is it, right? Right. Now what's given is the voltage drop across the 15 ohm resistance is 30 volts. This drop from here to here is 30 volts. That means the current flowing here must be 2 amp. If the drop here is 30 volts, the current flowing through this branch is going to be 2 amps, 30 by 15. So hit, no? Okay. We want to find the ratio of potential difference across this 15 ohm resistance and this resistance R. We want to find the drop across this to drop across this is what we want to find, right? Okay. See, there is 5 amps coming to this junction, there is 2 amps coming to this junction. Algebraic sum, that means there must be 7 amps leaving this junction. Whatever comes in must be leaving, right? Which means now across this 5 ohms, there is a 35 volt drop. There is a 35 volt drop across this, right? Now look at this loop very specifically. Look at just this loop, right? In this loop, there is a 35 volt drop across this. There is a 30 volt drop across this. There is a net drop of 100 volts here, right? 30 volt, 35 volts, 65 volts. That means the drop across this must also be 35 volts. 35 volts. We need to find what? Drop across this. By drop across this, 1 is to 1. Yes or no? I'll again explain. Kirchhoff's here. What else have I done here? This is Kirchhoff's only. It's just that I have stated Kirchhoff's arithmetically, but it is Kirchhoff's only. If I'm saying the total drop here is 100 volts in this loop, that's Kirchhoff's voltage law. What else that is? I've done Kirchhoff's law only, yaar. I've just not used symbolism. If I say the algebraic sum of the drops in this is 100 volts, is that not Kirchhoff? That's Kirchhoff only. I don't have to write an equation to apply Kirchhoff's law all the time, right? Isn't it? Ayush, check that. It's Kirchhoff's only that I have applied here. Let's look at number 4. Problem number 4. The problem number 4 is a network of this kind. 1 ohm, 1 ohm, 1 ohm, 1 ohm, 2 ohms, 13 volts, and it's labeled as A and B. And we want to find the potential difference VA minus VB. We seek to find VA minus VB in this problem, right? Obviously, once again, it's not a balanced bead stone. It's not a balanced bead stone, right? Nevertheless, if this is looked upon as 0 volts, how much is this? 13 volts. Yes, absolutely. This is 13 volts. This is 13 volts. Algebraic sum of currents leaving junction A must be 0. So this algebraic current, this and this must add up to 0. So from here to here, VA minus 13 by 1 plus VA minus VB by 1 plus VA minus 0 by 1 equal to 0. That's for junction A. That's for junction A. Right? Same thing we can do for junction B. This plus this algebraically must add up to 0. So this is VB minus 13. VB minus 13 divided by 1, right? This current. VB minus VA by 1. Plus VB minus 0 by 2. VB minus 0 by 2. Two equations, two unknowns. You can solve for VA and VB and therefore find VA minus VB. Got me? See, if I selected this as 20 volts, this will become 33 volts. VA will become this VA plus 13, VB will become this VB plus 13, or whatever 20. Everything will increase by 20, but the differences will remain the same. The differences VA minus VB will remain the same. You know what I'm saying? I'll repeat. Because there is no concept of an exact potential, dude. That's the whole idea in electrostats, electrical physics. It's the potential difference. I mean, I can label any point as any potential, and then based on that reference, I can assign potentials to other points or other regions. Right? Is there anything like an absolute potential? No, there never was. Again, I was hoping that you'll get it right all by yourself, right? Okay, now we have a network in problem number 5. This is 5 ohms. 15 ohms. Oh, 5 amp current hai. Okay, 5 amp current. There is 5 amp current. The resistance not known. Then there is this 5 ohms here. There is R here. There is a battery like this, 100 volts. There is 3 amps going this way, going into a resistor. Fine. There's 3 amps like this. There is 2 amps going through, again, some unknown resistance here. This is it, right? Right. Now what's given is the voltage drop across the 15 ohm resistance is 30 volts. This drop from here to here is 30 volts. That means the current flowing here must be 2 amp. If the drop here is 30 volts, the current flowing through this branch is going to be 2 amps, 30 by 15. So hit, no? Okay. We want to find the ratio of potential difference across this 15 ohm resistance and this resistance R. We want to find the drop across this to drop across this is what we want to find, right? Okay. See, there is 5 amps coming to this junction, there is 2 amps coming to this junction. Algebraic sum, that means there must be 7 amps leaving this junction. Whatever comes in must be leaving, right? Which means now across this 5 ohms, there is a 35 volt drop. There is a 35 volt drop across this, right? Now look at this loop very specifically. Look at just this loop, right? In this loop, there is a 35 volt drop across this. There is a 30 volt drop across this. There is a net drop of 100 volts here, right? 30 volt, 35 volts, 65 volts. That means the drop across this must also be 35 volts. 35 volts. We need to find what? Drop across this. By drop across this, 1 is to 1. Yes or no? I'll again explain. Kirchhoff's CA. What else have I done here? This is Kirchhoff's only. It's just that I have stated Kirchhoff's arithmetically, but it is Kirchhoff's only. If I'm saying the total drop here is 100 volts in this loop, that's Kirchhoff's voltage law. What else that is? I've done Kirchhoff's law only, yaar. I've just not used symbolism. If I say the algebraic sum of the drops in this is 100 volts, is that not Kirchhoff? That's Kirchhoff only. I don't have to write an equation to apply Kirchhoff's law all the time, right? Isn't it? Ayush, check that. It's Kirchhoff's only that I have applied here. Problem number 6. There is 3 ohms here. Okay. In this circuit, we want to be able to obtain the potential difference between points A and B. Potential difference between points A and B is all that we want to obtain here. Ulta? This one? Okay. In the diagram, it's just the opposite. Is this okay now, Rahul? Okay. 2 ohms, 3 ohms, 3 ohms, 5 ohms, 4 volts, etc. VA minus VB is what we are seeking to find. Now, suppose A is 0 volts. Right? Or what we could do is, let me take this as 0 volts instead. Let me take this junction as 0 volts because, that will be easier to deal with. If I took this as 0 volts, then this would be 4 volts. This would be 4 volts. This would be minus 2 volts. Yes or no? Now, if this is 4 volts, this would be 0 volts, 0 volts drop. Yes or no? What is the current flowing in this loop? 2 amps. 2 by 5 amps, isn't it? 2 volts is the drop divided by 5. So 2 by 5 amps is the current flowing through this. 2 by 5 amps is the current flowing through this. So then the drop across this, drop in this direction is going to be IR, right? 2 by 5 into 3 volts. Yes or no? IR is going to be the drop from this to this. 2 by 5 into 3, that means 6 by 5 volts is going to be the drop here. Now, if this is 0 volts and the drop is 6 by 5 volts, then this would be minus 6 by 5 volts. This point would be minus 6 by 5 volts, isn't it? Now, the current in this direction, 4 by half amp current. Yes or no? The current here is going to be half amp. 4 volts drop across 8 ohms. 4 by 8, half amp is the current, right? Now, if half amp is the current, then the drop from here to here is going to be half into 3. 3 by 2 volts is going to be the drop. Now, if this is 4 volts, then the drop being 3 by 2 volts, the potential of this point is going to be 4 minus 3 by 2. That's going to be the potential at B. So, which is 8 minus 3, which is 5 by 2 volts is the, and VA minus VB. VA minus VB is what we are seeking? Yes or no? So, VA minus VB is going to be, or VB minus VA, what is being? Okay, VB minus VA is what we are seeking here, is 5 by 2 plus 6 by 5. 25 plus 12, 37 by 12, 3.7 volts. 3.74 is the potential difference VB minus V. 5 by 2 minus 6 by 5. Right? So we have part of an electrical circuit given in the problem. Ohms, 20 ohms, 30 ohms. The potentials at A, B, C are, this is plus 30 volts, B is plus 12 volts, C is plus 2 volts. We want to find the current through the three resistors. Very simple, isn't it? All that you need to do is take the potential of this as X volts, then the algebraic sum of the currents in all the three directions, this and this is going to be 0. So in this direction we have X minus 12 by 20, right? X minus 12 by 20. Then in this direction we have X minus 30 by 10. Right? In this direction we have X minus 12 by 30. Yes or no? X minus 2 by 30. And this must add up to 0. You can find X. And once you know X, then the current through this X minus 12 by 20, etc. would be known to you. Right? Is about a cylindrical conductor, circular cross section, and this is the radial direction, the R direction, measured from the center of this, measured from the axis of the cylinder, and the specific resistance or the resistivity varies in the R direction as pi R. It's not uniform resistivity, right? At a distance R, a section will have resistivity pi R. Okay. We want to find the resistance in ohms of the conductor. Now the radius of this cylinder is capital R. The length is L. We want to find the resistance from this end to this end. All right. Now what we do is, I construct a concentric entity across the length, coaxial with the cylinder, of length L, this part. This just the shaded portion, this is of radius small r and of thickness dr. Radius small r and thickness dr. So all points on this are practically at the same distance small r from the axis, and therefore will have the same specific resistance. The area of cross section of this is going to be circumference 2 pi r into dr would be the area of cross section of this, right? So the resistance of this circular portion along the length L is going to be specific resistance pi r s into the length L divided by the area of cross section 2 pi r dr, right? 2 pi r dr, and all such coaxial portions are in parallel. So this is the resistance of this chosen portion. So the reciprocal of this resistance is what we need to add. The reciprocal of this resistance is 2 pi r dr divided by pi rl. That's the reciprocal of dr. Sum of all the reciprocals would be 1 by R equivalent. Sum of where small r runs from 0 to capital R. Yes or no? Right? That will be the reciprocal of the equivalent resistance. This gets cancelled, 2 will stay, R will get cancelled. So this is like 2R by L. 2R by L would be the reciprocal of the resistance. The resistance then equivalent is going to be L by 2R, now whatever that turns out to be. And this R is the radius, and this of course is the resistance. So let me call it dr prime. Dr prime. Yes, please. Yeah. See, if I take any two such coaxial cylinders, right, they are connected across the same ends. This is connected to one terminal of the battery. This whole portion is connected. This face is connected to another terminal of the battery. So all points on this would be at the same potential, right? All points on this would be at the same potential. Yes or no? So which means now if I look at two coaxial cylinders, they are connected across the same two ends of the battery. So they would have the same drop of potential, say E volts. Yes or no? So all these coaxial shaded portions would be across the same two ends, this face and this face. And both the faces, all points on a given face would be at the same potential. This is how it goes, right? Number 9. There is 6 ohms like this. There is 4 ohms like this. Ohms like this, 6 ohms like this, 5 ohms this way, we want to find the equivalent resistance across terminals A and B. All that you need to do is redraw the circuit commensurate with familiar topology, right? So this point is A. Now this point is, let's say, X. All of this is X. This is X and X, right? And say this is, and this of course will also be X. This would be Y, Y. And all of this would be B, right? So I start with A. From A to X, this 6 and this 4 are in parallel. So 6 into 4, 24 by 10, 2.4 ohms. So across A and X, 6 and 4 in parallel, 6 into 4 by 6 plus 4, 2.4 ohms, right? So from A to X, there is 2.4 ohms. Which is like 6 parallel with 4. 6 parallel with 4, right? A to Y, say let me call this Y, there is 12 ohms. A to Y, there is 12 ohms. And X to Y, there is 4 ohms and also 6 ohms. 4 and 6 in parallel, 2.4. So from X to Y, there is 2.4 ohms, right? From X to B, there is 5. From Y to B, there is 25. Yes or no? Between A and B, realize this is 2.4 by 12, 1 by 5. This is also 1 by 5. So X and Y must be at the same potential. Balance Wheatstone bridge between A and B. We afford the luxury of removing this then, if X and Y are at the same potential. And then 7.4, right, in parallel with 37. This is 7.4 in parallel with 37. So 7.4 into 37 divided by 44.4. That's the R across AB. How about it? Right? Whatever it comes out to be. I want to find, so all edges, this is a tetrahedron. This is a tetrahedron ABCD. So you know how a tetrahedron looks like, right? ABC is like one plane, and then D is out of that plane. D is out of that plane, right? So then these are the edges AB, AD, AC, DC, CB are the edges, and each edge is resistance R. Each of this is resistance R. DC is R. I imagine the current to be entering one of these points and leaving the other point, and what's the total resistance encountered in the process is what we need to obtain. It's okay, yaar. I mean, no big deal about it. You can wait till I finish this, right? Now, yes, so nice, so nice. Actually, do you observe that there is no way to distinguish between points C and D? Do you all understand that? See how I would perceive it. Different people will have different ways of, looking at it. It's like, think of a plane ACB and a plane ADB. If I swap these planes, will it make any difference in the resistors? Total resistance? No. Which means actually there is no difference between ACB lying here and ADB lying here, versus if ACB was this and ADB was this, it will produce the same resistance. Right? Sorry? Is it because the AB is the same to both? No, it's not because of the AB being same to both. It's not because of that. It's because they are interchangeable. It will make no difference in the resistance. That's why. I mean, or what I would do is, if I imagine the current to be entering B and leaving A, then, I'll have the same relationship that I had when it entered A and left B. So, no, it's not because AB is the same. It's certainly not because AB is the same. So C and D are at the same potential. Do you admit to this clause? You will have to, independently also cook up your ways of exploiting symmetry. And there are no cardinal rules for that. So if C and D are at the same potential, might as well disconnect this. Now think of it. This R and this R, 2R, that will be in parallel with this 2R, will be in parallel with this R. So 2R in parallel with 2R would be R, R in parallel with R would be R by 2.